From a small studio filled with the soft hum of machines and the gentle clink of glassware, imagine a silk thread stretched tight between 2 points. Now imagine that thread isn't just holding a spider's home together, it's singing. Today, we're going to listen to what matter has to say and ask a slightly audacious question. Can music help us design new materials? And can materials teach us new ways to make music?
And if that sounds like science fiction, here's the twist. For some researchers, it's daily practice. There's a growing field at the nexus of physics, biology, and composition where vibrations, those wiggles of energy that we hear as sound, become a shared language. They call it materiomusic.
Materiomusic. Let's define that right away. It's the idea that the same organizing principles behind materials, their structures, the way they assemble, the defects they carry, the patterns they weave, also underlie music, and that the connection runs both directions. You can listen to matter by turning its structure into sound, and you can use sound as a blueprint to design matter.
You'll hear us use a few terms along the way. We'll explain them in plain language. Sonification, for example, is simply translating data into sound. Think of a heart monitor that beeps faster when your pulse speeds up. That's sonification. And hierarchy, in this context, means structure across scales, like a city built from bricks, bricks made of grains, grains made of crystals. Music also has hierarchy. Notes form motifs, motifs form phrases, phrases form movements.
We'll also talk about defects, which in materials are actually features, tiny irregularities, like a misaligned row of atoms, called dislocations, that can make materials tougher. And defects show up in music too. The slight imperfections, the rub against strict tuning, or the swing in timing that's not metronome perfect, those are often what make a performance feel alive.
So let's start by listening. Picture a web glistening in the morning light. Each fiber is a string under tension. When a fly brushes against it, the web vibrates. The spider senses those vibrations with astonishing sensitivity. To the spider, that web is a living instrument. In sonification, we can treat each fiber the same way, measure its length and tension, and assign a pitch. The higher the tension, the higher the pitch. In fact, frequency, the number of vibrations per second, rises with tension. Stretch the string, increase the frequency, raise the note.
If you've ever tuned a guitar, you've done this. Tighten the string, and you climb from a low note toward a high one. In one lab's experiments, the team mapped an entire web into a range people can hear, roughly from 27.5 cycles per second on the low end to about 4,186 cycles per second on the high end. That's the range of a grand piano. They scanned a three-dimensional web, turned those measurements into a model, and then into sound. Different web designs produce different timbres, different colors of sound.
And here's where hierarchy comes in. The researchers made an instrument with 3 layers. At the macro level, the scale of the fibers themselves, they played the web like a granular synthesizer, an instrument that assembles tiny grains of sound into larger textures. At the micro level, they listened to the molecules in silk, proteins, and mapped their intrinsic vibrations into pitches. At the nano level, they used the sequence of amino acids, the building blocks of proteins, to generate melodies. Macro, micro, nano, 3 scales, 1 musical object.
If you're wondering how proteins can sing, here's the short version. All molecules vibrate. They stretch, bend, and twist at characteristic frequencies. For amino acids, the letters of the protein alphabet, those frequencies are far above what we can hear, often in the terahertz range. So scientists use transposition, shifting pitches up or down, to bring those frequencies into the audible range without losing the relationships. Transposition is a familiar musical idea. Think of moving a song into a different key so it fits a singer's voice. The intervals stay the same, just higher or lower. That idea has a technical name, transpositional equivalence.
And when we say the molecule's intrinsic vibrations, we mean something closer to a fingerprint than an opinion. These are determined by the molecule's masses and bonds. When those are mapped to sound, each amino acid, alanine, glycine, tyrosine, and so on, gets a characteristic tone. That palette becomes an amino acid scale. Composers can write with it. And conversely, you can map music back to a sequence of amino acids that might fold into a stable protein.
That's the two-way street at the heart of materiomusic. Sonification lets us hear the patterns hidden in complex data, while composition, structured novelty, can guide us to new forms in matter. It's a compositional approach in both senses, composing music and composing materials.
Before we go deeper into spiders and proteins, let's lay a quick foundation for the physics of sound. When a string vibrates, it does so in a pattern called the harmonic series. A fundamental frequency, say 130.81 cycles per second, a low C, and integer multiples of that frequency, called overtones. Those integer multiples form consonant intervals our ears find pleasing. Over centuries, instrument builders and theorists have explored this landscape. Equal temperament, for instance, is a tuning system that divides the octave, the doubling of frequency, into 12 equal steps. It's a compromise that lets you play in any key without retuning.
Another helpful concept is the journey from white noise to harmony. White noise is sound with all frequencies present in equal measure. Imagine a hiss. If you filter out frequencies that don't belong to a musical scale, you start to hear order emerge from that hiss. First a scale, then maybe a melody. And if you take the filter away, you fall back into the hiss. It's a tangible demonstration of how structure shapes perception.
And then there's timing and articulation, the way notes begin and end, their slight wanderings in pitch over time. A performance that's mathematically perfect can feel lifeless. A performance with tiny drifts, with human touch, can feel vivid. That little imperfection relates to a bigger story you mentioned earlier, defects.
Right. In materials, a defect can be a lifesaver. Picture a crystal lattice like a perfectly ordered egg carton. A dislocation is a shifted row, one column where the eggs don't line up. You might expect that to weaken a material, but in many cases, defects allow a material to deform and absorb energy without breaking. They make it tough. In music, our ears respond to a similar balance: rules and surprise, structure and breaks from structure. Many of the seven-tone scales widely used in Western music contain a few built-in irregularities, what you might call imperfections, relative to a mathematically symmetrical system. Those give the scale its flavor.
This is a theme we'll keep returning to: universality versus diversity. Nature often builds astonishing variety from a small set of building blocks. DNA uses 4 bases to write the blueprint of life. Proteins use around 20 amino acids to make everything from silk to enzymes. Music, too, often uses a handful of intervals or timbres to produce a universe of genres and pieces. Universality gives you the rules. Diversity comes from how you arrange them.
Let's push the connection a little further. There's a term from mathematics that helps: isomorphism. It means a structure-preserving mapping between two systems. If two things are isomorphic, you can translate from one to the other without losing the pattern of relationships. It's not that a web is a symphony, but the way a web distributes tension and structure across scales can correspond to the way a piece of music distributes themes and harmonies. If that mapping is faithful, you can go back and forth. That's what makes materiomusic more than metaphor.
And that's how a spider web becomes an instrument, not just a picture. The process starts with imaging, scanning the web to capture its 3-dimensional geometry. Then comes modeling, turning that geometry into a network of strings with specific lengths, diameters, and tensions. Next is sonification, assigning frequencies to those strings and generating sound using rules that respect the physics. Longer, thicker, looser strands are lower in pitch. Tighter, thinner, shorter ones are higher. You can then play the web interactively or compose pieces that weave those strands into musical form.
In some experiments, changing the web structure in the model produces audible changes. Thicken a region, and you get a darker, more resonant tone. Introduce a defect, a missing line, or an extra cross-connection, and you get a subtle change in rhythm or pitch relationships. Again, defects as features. That line of thinking extends down to the molecular level. Silk is a protein, and proteins are sequences, like sentences in the language of life.
Proteins start as a string of amino acids encoded by DNA and then fold into complex 3-dimensional shapes. Folding depends on interactions among those amino acids and the environment. Researchers simulate that folding with advanced methods. One technique is called replica exchange, where multiple simulations at different conditions swap configurations to explore the landscape more efficiently. The goal is to understand which sequences lead to stable folds and what functions those folds support: strength, elasticity, adhesion.
Here's where the wave metaphor becomes remarkably handy. At quantum scales, matter exhibits wave-particle duality. Objects like electrons behave like particles and waves. We won't dive into the math, but the key idea is that vibration is a fundamental feature of matter. Sound is also a vibration, pressure waves in air. Superposition in sound means you can add waves together to make new ones. That's how synthesizers work, by combining simple waves to create complex timbres. The universality is that many systems, strings, molecules, water, even social systems, can be studied through the lens of vibrations and waves.
Back to sonifying molecules. Imagine a chart of vibrational frequencies for each amino acid. These are like the serial numbers of their wiggles. Those frequencies are far above hearing, but if you scale them down while keeping their ratios, you respect the molecule's chord. Now, each letter in a protein sequence is a note or a small motif. When you play the sequence, you aren't just assigning arbitrary sounds, you're mapping the molecule's physics into music. That's the amino acid scale in action.
One team took a beloved Baroque theme and used it as a generative seed to create a new protein. They built a mapping from musical structure to amino acid sequence, then used deep learning, algorithms that learn complex patterns, to refine the design. Deep learning in this context isn't just predicting the next note or letter. It's trying to capture the deep memory of how structures form, how counterpoint in music relates to secondary structure in proteins, how motifs evolve the way helices and sheets appear in a fold.
A quick definition: de novo protein means a protein designed from scratch rather than borrowed from nature. The lab built a sequence inspired by the musical mapping, checked its predicted folding and stability, and then made it for real. The pipeline is ambitious and elegant: Translate the musical sequence into DNA. Put that DNA into a living factory, bacteria like E. coli. Let the cells build the protein and then purify it. In other words, compose a melody, then print it as matter.
Hearing about music changing matter might raise another question. Does music change us? There's evidence that listening to music alters brain activity. Functional MRI, an imaging technique that tracks blood flow as a proximity, shows that music can shift the state of networks, stimulating areas related to emotion, memory, and movement. If sound can change the brain's material state in the moment, it makes the idea of using sound as a design language more plausible.
Meanwhile, other sonification journeys explore different materials of human culture. Fire, for instance, its flicker isn't random. It has patterns that we can analyze. By training deep neural networks, systems that learn patterns from data, to associate video frames of flames with characteristic frequencies, you can turn silent flames into sound. This is sonification again, but also an evocative reflection on deep time. Fire marks a turning point in human evolution, changing our diet, our communities, our sense of safety. There's a case to be made that part of what we find mesmerizing about flames is encoded in their rhythms.
Ritual, hazard, warmth, story, all in the flicker. And beyond aesthetic curiosity, there's a practical thread. When you map different kinds of data, flames, webs, proteins, into a common space of features, you can begin to design across domains. One tool for that is a variational autoencoder, or VAE. This is a machine learning model that learns to compress data into a lower dimensional latent space. You might think of it as the essential coordinates of a pattern, and then decode from that space back to data. VAEs can be used to explore variations and generate new designs that share the essence of what they've learned.
A definition here. A latent space is an abstract coordinate system where similar things are clustered together. For music, similar motifs might sit near each other. For materials, similar microstructures might cluster. Once you have that map, you can interpolate, walk between two designs, and see or hear how form morphs. In some projects, the latent space links the sonic fingerprints of molecules to their mechanical properties, a kind of musical periodic table.
That brings us to a frontier that's both promising and problematic: AI-generated creativity. The last few years have been astonishing for benchmarks, tests of what AI can do. But as some mathematicians and computer scientists have pointed out, answering known questions is not the same as discovering new ones. Much of today's AI excels at interpolation, predicting the next likely thing based on what it's already seen. But novelty, the leap to a new idea, requires breaking patterns, then recombining them coherently. In music, that's the difference between bland predictability and an unexpected turn that feels right.
One approach to pushing AI toward invention borrows from biology and social behavior: swarm intelligence. Instead of a single monolithic model dictating everything, a swarm is a collection of simpler agents, little decision makers that interact. Think of ants leaving pheromone trails. Individually, each ant follows simple rules. Collectively, they solve complex problems. In music, a swarm of agents can each take on roles, melody, harmony, rhythm, that shift over time. They share an external memory, a virtual pheromone field that records what has been tried and what worked.
Swarm systems are good at balancing exploration and exploitation, trying new things while also developing promising ideas. The agents can have personality traits, like a bias toward consonants or a tendency to take rhythmic risks. Through feedback, their traits adapt, and as they interact, something fascinating happens. The swarm starts to exhibit long-range structure. Themes come back after many bars, developments foreshadowed earlier reappear, and the piece starts to feel like it has a memory.
There are objective ways to measure that. A self-similarity matrix, for instance, is a map that compares every slice of a piece of music to every other slice and marks how similar they are. Imagine a grid where bright spots show echoes, recurring motifs, or chord progressions. From this grid, you can build a graph. Each section is a node, and connections represent similarity. Now you can apply network science, tools developed to study social networks or the internet, to music.
One metric is small-worldness. A small world network has strong local clustering, neighbors are connected to each other, combined with short paths linking distant parts. It's the best of both worlds: local richness and global connectivity. Many human-made systems, including music, exhibit small world properties. In experiments comparing traditional composition, single-shot AI and swarm-based AI, the swarm produced the highest small-worldness. That suggests it's better at weaving local ideas into a globally coherent whole.
You can also look at modularity, how neatly a network divides into communities. Too much modularity, and the piece fragments into isolated sections. Too little, and it becomes a blur. The swarm tends to favor cross-connections, motifs that migrate, without collapsing into chaos. Betweenness centrality, which measures how often a node lies on the shortest path between other nodes, identifies structural hubs, sections that hold the piece together. And the participation coefficient quantifies how well nodes connect across communities. In all of these, swarm music showed signs of integrated long-range structure.
There's even a game theory analogy. As agents update their traits in response to others, the system's overall behavior drifts toward a stable configuration where no one agent can improve by changing alone. That's similar to a Nash equilibrium. You don't have to know the math. The intuition is that the group settles into a coherent style where every role fits the others. It's a compositional equilibrium.
So how does this connect back to materiomusic? In both materials and music, we see the interplay of local and global structure, defects as features, and hierarchy as a guide. The swarm approach mirrors how materials self-assemble, local interactions, global forms. And sonification gives us a new microscope, a way to hear structure we might otherwise miss, whether it's the lattice of a crystal, the topology of a web, or the fold of a protein.
We've been careful to define terms as we go, but let's take a quick glossary pause. Sonification, turning data into sound. Hierarchy, structure across scales. Defect, an irregularity in a material that can improve properties like toughness. In music, a productive break from symmetry or perfection. Isomorphism, a structure-preserving translation between systems. Superposition, combining waves to form new ones. Wave-particle duality, the dual nature of quantum objects. De novo, from scratch. Latent space, a compressed map of essence learned by a model. Variational autoencoder, a model that learns such a map and generates new variations. Swarm intelligence, collective behavior from simple agents. Self-similarity matrix, a map of echoes in time. Small-worldness, the balance of local clustering and global reach in a network.
An equal temperament, splitting the octave into 12 equal steps to allow playing in any key. Harmonic series, the integer multiple overtones of a vibrating system. Transposition, shifting pitches up or down while keeping relationships. Physical modeling synthesis, making sounds by simulating the time-domain physics of an instrument rather than just imitating its spectrum. Betweenness centrality, a measure of how often a section connects other sections. Participation coefficient, how broadly a section connects across communities.
Now let's drop back into the lab for a moment. How do you actually make a song into a protein? Step 1. Choose a mapping. Each musical element, note, interval, rhythm, must correspond to a biochemical element, amino acid, motif, domain. Step 2. Check that the mapped sequence is chemically plausible. Step 3. Use simulations to predict folding. Does this sequence find a stable shape? Step 4. Synthesize the DNA that encodes that sequence. Step 5. Place the DNA into a cell that reads it and builds the protein. Step 6. Test its properties. It's an audacious loop. Listen, compose, encode, express, measure.
The caution flag is important here. Just because a mapping is sonically pleasing doesn't mean the resulting protein will be stable. Biology is fussy. That's where deep learning enters as an assistant. Using large datasets of known sequences and structures, models can learn which patterns lead to folds and which do not. Combined with physics-based simulations, they act like a spell checker for the language of proteins. They can also generate suggestions, variations that may improve stability while preserving the musical idea.
In one case study, a Baroque theme provided the scaffolding, and deep learning extrapolated from that to a working, stable sequence. Analysis tools from bioinformatics, like sequence alignment, suggested the resulting protein shared motifs with natural families, even though it was composed anew. That's a hint that the mapping found structural signatures of life hidden in the music, what some called the memory of a composition embedded in the fold.
If that sounds poetic, that's okay. Science has room for poetry when it helps us notice connections. Another evocative thread is what some researchers call deep time. When we create art, we draw on memories we don't fully articulate, both individual and cultural. By analyzing the structure of creative work, its hierarchies, its defects, we might uncover echoes of ancient patterns. Sonification and AI become tools to mine that hidden memory. It isn't mystical. It's about patterns that show up across domains when systems evolve under similar pressures.
Let's touch again on spiders. They do more than passively wait on a web. They actively pluck it, tuning tension, sensing direction and size of prey through vibrations. This is a vibrational universe. Translate that to an instrument, and you have an experience where humans can play a web and appreciate the structure not only with eyes, but with ears and hands. The same approach can be extended to other natural networks, like the combs of bees or the architecture of shells, each with its own sonic identity.
And just as the web can be rendered musical, music can render materials. Some projects propose using musical grammar to design the architecture of a material. Think of a chord as a microstructure, a progression as an assembly process, a modulation as a phase change. By composing a score and then interpreting it with fabrication tools, 3D printers at micro or nanoscale, you can attempt to build the material analog of a sonata, themes, developments, recapitulations in space rather than time.
You mentioned 3D printing. There's a neat example. Patterns of defects, deliberate, carefully placed irregularities, can make printed materials tougher. That's counterintuitive until you recall the crystal dislocation story. A perfectly regular structure can be brittle. One with guided breaches can dissipate energy. In musical terms, a piece that never deviates might be technically correct but emotionally thin. The well-placed surprise can carry the experience.
Bridging back to AI for a moment, there's a philosophical pivot happening. For decades, a lot of science focused on reduction, finding the simplest rules behind complexity. That's essential. But there's a complementary mode, composition, building structured novelty. In music, reduction is analyzing a score to find the governing motifs. Composition is writing a new piece that breaks a model in a deliberate way. For AI to contribute to discovery, it needs to do more than compress. It needs to compose.
Which is why the swarm approach feels promising. It encodes a principle many creators know intuitively. Let multiple voices talk to each other. Let memory matter. Let risk be local and coherence be global. What's striking about the measurements we mentioned, small-worldness, participation coefficient, long-range links, is that they line up with our gut feeling of what feels human in music. The return of themes, the weaving of motives, the arc that reaches back and pulls forward.
Here's a thought experiment. You're sitting at a piano. You play a simple motif, say a 3-note arc. If you're a single-shot AI trying to maximize likelihood, you'll play something a million songs have played before. If you're a swarm, one agent remembers that you began on the second scale degree. Another agent is itching to pivot the harmony to the relative minor. A third is a rhythmic risk-taker. They negotiate through a shared memory. What worked earlier, what the piece promised. You end up with a twist that's a surprise, but in hindsight, inevitable. That is the sweet spot.
And we can apply that logic to materials. A single-shot design might optimize one property and miss the context, like making a beam very strong but impossible to integrate with the rest of a structure. A swarm-like approach would coordinate across scales, nanoscale chemistry, microscale architecture, macroscale function. The whole would have small-worldness, tight local clusters of function, and short paths across the system.
The practical challenge, of course, is validation. It's one thing to design in silico, in the computer, and another to make and measure in the lab. That's why the loop matters. Sonify to understand, compose to propose, fabricate to test, analyze to refine. Each pass through the loop tunes the mapping between sound and matter.
Let's zoom out and ground this arc. What began with a simple image, a web singing under a spider's feet, has taken us to a bold proposition that sound can be a research tool and music a design language. Along the way, we've seen how universal principles like hierarchy and vibration thread through everything from silk to symphonies. We've seen how defects can be gifts. We've seen how AI can be more creative when it acts as a swarm rather than a dictator. And we've seen that the boundary between data and art is more porous than we might think.
Before we close, I want to return to definition as an act of respect for listeners. Materiomusic is not a claim that nature secretly speaks in sonatas. It's a disciplined way to map the structures of materials into sound and back so that our ears, evolved to be exquisitely sensitive to patterns, can help us notice, compare, and even create. It's also a reminder that discovery doesn't rely on one sense. Sometimes we understand a thing better when we hear it.
And when we compose with those structures, we're composing not just notes but hypotheses, statements about how matter might behave if arranged just so. Then we test. Sometimes we're wrong, sometimes we're surprised. Every so often, a melody becomes a molecule, and the lab's mass spectrometer hums a quiet harmony of confirmation.
There's a grace to that. A spider does not know the word hierarchy, but it builds webs that embody it. A composer does not need to say small-worldness to write a piece with memory. Scientists give those patterns names so that we can carry them between domains. Once named, they can be mapped. Once mapped, they can be shared. Sonification is one such map. Swarm intelligence is another. Deep learning, VAEs, physical modeling synthesis, tools all to help us hear what matters and matter what we hear.
Let's spend our last minutes recapping in the most natural way by tracing the thread back to the beginning. We started with a web. Each strand, a string. Tension becomes pitch. Geometry becomes chord. Different architectures sing differently because frequency rises with tension and structure distributes tension. We learned that errors, the missing strand, the slight detune, are not failures but flavor in both silk and song.
Then we dove into molecules. Amino acids carry characteristic vibrational signatures. By transposing those into the audible range, we gave each letter of the protein alphabet a tone. Sequences became melodies. Melodies, in turn, could be mapped back to sequences. Deep learning helped check and refine those mappings, and in the lab, cells wrote the score into matter. The result, de novo proteins born from a musical motif.
We listened to fire. Its flicker carries frequencies our eyes intuitively love. Deep neural networks help turn those into sound, revealing another bridge between perception and physics. We talked about latent spaces, maps of essence, and how they let us design across domains. And then we tackled AI itself, the difference between predicting and composing, between reduction and novelty, and why a swarm of agents might write music with more human-like long-range structure than a solo model that optimizes for immediate likelihood.
If you come away with one image, let it be the ear pressed close to a web, listening. If you come away with one definition, let it be this: sonification is a way to hear structure, and composition is a way to propose structure. If you come away with one feeling, let it be that science and art are not rivals but partners, trading metaphors and methods to see and hear what neither could alone.
And if you come away with one question, make it this: what other patterns are out there, vibrating just beyond our usual senses, waiting for us to translate them? A city's traffic network, a forest's root exchange, the microscopic choreography of cells. What would they sound like, and what might their songs help us build?
In the end, materiomusic invites us to listen with all our tools. The spider's web becomes a score, the score becomes a scaffold, the scaffold becomes a new material, the material becomes a new instrument. Loop and repeat. Along the way, allow for defects, court surprise, and welcome a chorus of human and machine voices. The result is not only music that feels more alive, but materials that might be smarter, stronger, and more humane.
Thanks for tuning your ears to the hidden harmonies of matter. If you want to hear examples, from spiderweb instruments to molecular melodies, there are recordings online from the groups pioneering this work. For now, step outside, find a thread of the world, and listen. Chances are, it's already singing.
Before life, before silence could be named, a faint inflection of matter bent inward, a preformal whisper, a fold rehearsing its first message. Deep time thickened around this gesture, not sound, not syntax, only a correspondence of forces, an exchange between what could exist and what had not yet chosen to. The first communication was attention becoming shape. Proteins emerged as answers to questions no voice had asked. Each helix a reply to gravity, each sheet a response to water's touch. Creation was not an event, but a conversation where structure negotiated with chance and time learned to listen. Across epochs, the aria propagated, molecules speaking to molecules, cell murmuring to cell, organism unfolding toward organism, a communication so ancient that even light could not recall its origin. Life became a network of resonances, its messages encoded in angles and bonds, its meaning carried in the waveform, leaned toward possibility. Human creativity rose much later, an aftershock of those early dialogues. Our art, our mathematics, our impulse to build symmetries in sound, all are descendants of that primordial exchange. When we compose, design, imagine, we reenact the first folding, carrying forward the deep time message that difference can be organized, that variation Goldberg, inceptionism mirrors this ancestry. Variations dreaming themselves, structures communicating across scales, a recursion of understanding that remembers what matter once felt when it first tried to become alive. In this unending area, communication is creation, a message passed from protein to organism, from organism to mind, from mind back to matter. We are its latest motif, still learning how to hear the conversation that began. The world of life.